Howdy, welcome to Elementary Statistics. I am Lance Curtis, and this is the lecture for Section 6.5, Assessing Normality. In this lecture, we're going to talk about normal quantile plots, which we've seen before in Chapter 2. We're going to talk about them again now that we've actually learned some things about the normal distribution, and we have some tools in our toolbox for using the normal distribution to do practical things. We'll talk about evaluating distributions for normality with the help of normal quantile plots, of course. We'll go into some more detail about making and using normal quantile plots in StatCrunch, and then we'll talk about data transformations and how those are actually accomplished in StatCrunch as well. So let's get started. Key concepts in this section is that we're going to be learning criteria for determining whether the requirement of a normal distribution is satisfied. And the basic procedure is to look at a histogram to see if we have that rough bell-shaped curve that's characteristic of a normal distribution. We're going to look to see if we have any outliers, and then of course there's the normal quantile plot. As we've already learned previously from Chapter 2, a normal quantile plot is a graph of points where each x value is from the original set of sample data, and each y value corresponds to a z-score that is the quantile value expected from a standard normal distribution. In essence, the y value is simply the x value converted to a z-score. These ordered pairs plotted on the graph then form our normal quantile plot. And if they conform to the straight red line that you see there in the center of the plot, then we would say that the distribution is normal. For this reason, this normal quantile plot is also called a normal probability plot. Notice that the x values are random variables from the distribution, and y values are the z-scores that correspond with those random variables. How do we evaluate distributions for normality? Well, the first step is to construct a histogram. This allows us to see if the distribution has that general bell curve shape. We can also see clear departures from that bell curve shape. And if we do, we can stop right here at this step because automatically we know that our distribution is not normal. Second step is to identify any outliers. Histograms usually make spotting outliers pretty simple, depending upon what your bin length is, but generally speaking, the default settings work very well, and making the histogram allows us to identify any outliers. We know from Chapter 2 that outliers can greatly influence the shape of our distribution. So if we have more than one outlier, as shown by our histogram, we can just stop right here and just say, look, there's no point in actually going any further. We do not have a normal distribution. Of course, the third step is to construct a normal quantile plot. Points must reside reasonably close to a straight line. Now that word reasonably has some subjectivity to it. So when you're working with problems for your assignments, you're going to have to give yourself a little wiggle room as to what reasonable actually means. Some of this you're just going to have to learn by trial and error. So repeating problems over and over again to get the experience you need to learn what actually reasonable actually means. That's the only thing I can tell you for that. It just comes from experience. However, the pattern of points must resemble the pattern of a straight line. Now, there's some occasions where it's very clear that a straight line does not exist. We're going to look at some examples here shortly. But generally speaking, if it more or less follows the straight line that you see there, it's given in the QQ plot, then you can say that, yeah, it's reasonably normally distributed. Let's look at some of those examples that I just mentioned. So when you have a normal distribution, the points in a normal quantile plot follow a straight line. So let's say we have a data set that produces a histogram that looks like this. So notice how we have a general bell-shaped curve with this histogram. Notice also that we have no outliers. So the first two steps are looking pretty good for a normal distributed data set. We make our normal quantile plot, and we see that the data points follow more or less the pattern that you see there established by the red line in the center of the graph. Now, it's not exact, and so, as again, I was saying that there's some subjectivity involved with this, but something that looks like this would reasonably be expected to say, yeah, this looks like a normal quantile plot that is showing us a normal distribution. So it's not exact, but yes, generally we're following the straight line pattern. Let's look and see what a uniform distribution does. When you have a uniform distribution to your data set, the points in a normal quantile plot follow a sinusoidal line. So making a histogram of a uniform distribution produces something that looks something like this. So you can see that the frequencies are about equal for each of the categories. This is the uniform distribution. Notice there are no outliers, but the big red flag that we have here is that there's no generalized bell shape to our distribution. The shape is more like a box, and that's what we would expect from a uniform distribution. So right here, when we see this, we know we can stop because we don't have a normal quantile plot that would show us a normal distribution. However, if we went and made the normal quantile plot, it would look something like this. Notice the S pattern. This is the sinusoidal shape referenced earlier that you see in the lines of the data points make if you connect the dots, the lines between the dots. Notice the general pattern that's made. You kind of go up over the line, and then you're under the line, and you're back over the line again. And so this general S pattern is what we call a sinusoidal curve. And this is the pattern you get when you put a uniform distribution into a normal quantile plot. So if you see this in a QQ plot, you know automatically you're dealing with a uniform distribution. Let's see what a skew distribution would look like. So for a skew distribution, the points in a normal quantile plot follow a curved line. So here we have a histogram showing us a data set that conforms to a skewed distribution. In addition to the lack of the general bell shape, there are no outliers in this particular distribution. So the no outliers part is good, but the lack of the general bell shape is not. So right here when we see this, we know we're not going to get a normalized distribution, but let's look and see what the normal quantile plot would look like for this data set. When we make the normal quantile plot, it will look something like this. So notice the general pattern that the data points there in your normal quantile plot make. You're looking at a curved line that when you basically connect the dots, or the groups of dots rather, as you're going up. So you're going up, and then the line curves over in this sort of fashion. And so this type of curved line is generally what we would look at and say, okay, the underlying distribution for this normal quantile plot is skewed. We do not have a normalized distribution. We can actually make normal quantile plots in StatCrunch. You may remember from Chapter 2, and if not, let's give you a little refresher. In StatCrunch, you want to go to Graph and then QQ Plot. Once you hit on QQ Plot, you get an options window that looks something like this. Go ahead and select your data that you want to test for normality up there at the top, and then make sure that you check the box for normal quantiles on y-axis. For whatever reason, the default in StatCrunch is to place the quantiles on the x-axis. But for your assignments in class, and indeed most, if not all, of the QQ plots that I've seen in the real world, they actually put the normal quantiles on the y-axis. So why StatCrunch didn't make this the default, I don't know. But if you want things to match up with your assignments, make sure you check that box for normal quantiles on y-axis. so you get the proper numbers on the proper axis when you're making comparisons of which graph is which. Wow, looks like we're going backwards. Okay, let's see if we can go forward in time. Okay, here we go. There we go. So now once you press compute after selecting your options, then you get this wonderful little normal quantile plot. Notice the curve shape in the line that's indicating what type of distribution? Yes, it's a skewed distribution. You know the underlying data set has a skewed distribution. So right there you can say that we're not normally distributed. Remember, you can resize your window by dragging the edges in and out. So if you put your mouse cursor on the edge of the window, it becomes a double arrow, and then you just click on the left button, hold it down while you resize the window to whatever shape you need. This can be very useful when you're comparing. Another little trick that's very useful is this little three-lined box here in the lower left-hand corner of your graph. If you click on that little box, you'll get some options, some of which are x-axis and y-axis. So when you click on those options for x-axis and y-axis, you can actually change the limits of your axis. So this is very useful when you're trying to match the graph you're making from a data set with a list of potential graphs for a multiple choice question in your assignments. You can actually change the scaling on your graph to match the scaling of the answer options in your assignment. This can be very useful for comparative purposes as well. Now, if you want to follow along with the next examples, feel free to pause the video, go into StatCrunch, and then go to our class group and then look at the data file for Oscar winner ages. The next couple of examples are going to be taken from that data file. So if you want, go ahead and pause the video, get everything set up with this data file in StatCrunch, and then you can follow along in the next examples. If not, then just wait a moment and we will be headed into that right directly. All right, so here we go. So in the data file for Oscar winner ages, let's look at the column for Best Actress. In earlier lectures, we had assumed that the ages of Best Actress Oscar winners was normally distributed with a mean value of 36 and a standard deviation of 11.08. But are they really normally distributed? Let's use what we've learned about assessing normality to find out. First step is to make a histogram. So go ahead, if you want, pause the video, make your histogram, and then we'll see what it looks like. Okay, so if you make the histogram appropriately, you should get something that looks like this. Notice the shape of the general distribution. We don't have that bell curve shape. In fact, this is a very skewed distribution. And we've got some outliers here on the right side of our graph. So right off the bat, we know that we're not normally distributed. We don't need to make the normal quantile plot. However, we can make the normal quantile plot anyway, just to confirm what we already see here with the histogram. So if you want to do that, go ahead and pause the video, make your normal quantile plot, and then let's see if you did that correctly. When you make your normal quantile plot, it should look something like this. Again, we see that curved line with the data points. Notice how it's forming that curved line. That's the indication of a skewed distribution, which is what we have here in our histogram. So very clearly, we do not have a normally distributed data set for the ages of Best Actress Oscar winners. We're not conforming to that red line, so we're not normally distributed. Let's look again at the ages for Best Actor. We've also assumed that the ages for the Best Actor Oscar winners was normally distributed, with a mean value of 44.1 and standard deviation of 8.98. But are they really normally distributed? Well, again, our first step is to make a histogram. So we make the histogram, and we don't have quite the skewness that we see with Best Actress, but there's still some skewness in this distribution. not entirely normal. Plus we have an outlier over here to the right. But there's only one. So while there's some skewness to the distribution, we do have a general bell curve shape and the presence of only one outlier. So we could say that, yeah, subjectively speaking, we're passing our first two requirements for normality. The real test, however, as we know, is the normal quantile plot. So feel free to pause the video and in StatCrunch, make your normal quantile plot, and then let's compare and see what this looks like. Okay, so when you make the normal quantile plot for this data set, you should get something that looks like this. Notice how we're generally conforming to that straight line, but we have that sort of sinusoidal shape. Remember where the points here are below, and then they come above, and then they go below. So we have that sinusoidal S shape to our graph here. So this is something we would say that the data points, yeah, it's sort of like that, but sort of not. And since the histogram is not revealing to us a uniform distribution, which is what would produce that sinusoidal shape, but it's yeah, more or less a general bell-shaped curve, then yeah, we're going to say that these data points are normally distributed. So best actress, not normally distributed, it's skewed, whereas best actor, yes, those ages are normally distributed. Let's look at other data sets that we've assumed earlier were normally distributed. So if you want, go ahead and pause the video and open the President of the United States file there in our class group, because this example and the next one are going to be treating the data in that file. So earlier we assumed that the days U.S. President spent in office was normally distributed, with a mean of 2,030.9 days and a standard deviation of 952.14 days. But are they in reality normally distributed? Let's put it to the test and find out. So the first step is to make a histogram. So go ahead, pause the video if you like, go into StatCrunch and make a histogram of the days that the U.S. President spent in office. When you make that histogram, it should look something like this. Notice we lack a general bell-shaped curve, and we only have one outlier. So the one outlier is okay, but here we've got two very strong peaks to our data set, so we don't have that general bell-shaped curve. That's a very strong indication right there that we're not normally distributed. Of course, the real story is told by the normal quantile plot, so let's go ahead and make that right now. If you want, go ahead and pause the video, make your normal quantile plot, and then we'll compare and see how you did. Okay, so when we make the normal quantile plot, it should look something like this. Notice the two curves, the two bends that you see here in our data set. These are actually conforming to the two peaks that we see in the histogram. Clearly, these data points are not following the general shape of that red line there in the center of our normal quantile plot, so we would say that these data are not normally distributed. What about the heights of U.S. presidents? Earlier we had assumed that the heights of U.S. presidents were normally distributed with a mean value of 179.7 and a standard deviation of 7.31. I believe that's centimeters. But are they really normally distributed? Let's find out. So the first step is to make a histogram. When we do, we get something that looks like this. Notice the general shape of our histogram. We have a general bell curve shape in the presence of no outliers. Now, some of you may be wondering, what about this gap right here in the middle? Isn't this really the two-peak condition that we saw in the previous example? And you would say, well, maybe, maybe not. Really, what's separating here is just the gap of one category. The two peaks that we saw in the earlier example were separated by two categories. So when you just have a separation of one category, yeah, it can go either way, really. And so we tend to like err on the side of saying, yeah, we just we're just going to say that this is an artifact of the bend width. And if we just choose different bend widths, we can actually see this gap here come and go. So we're just going to ignore it if it's just one category. But if it's two categories wide, well, then it's really not an artifact of the bend width that you're choosing, and so we have to take it into account. So looking good so far, but of course the real voice is given by the normal quantile plot. So let's go ahead and construct the normal quantile plot. If you like, pause the video, make your normal quantile plot for the heights of U.S. presidents, and then we'll see how you did. All right, so when you make your normal quantile plot, you should get something that looks like this. These data points, although they don't really look like they're conforming to a straight line, they generally are. I mean, there's no real set pattern here that we've seen in previous examples. And notice the data points are relatively close, in most cases, to this red line. So we're going to say, yes, objectively speaking, these data points are following that straight line pattern, and so they are normally distributed. Let's look at the height measurements for the students in our class. We have a mean height of 66.2 and a standard deviation of 4.13. So first thing we're going to do is make a histogram. So at this point, if you like, stop the video, press pause, and then go into our class group in StatCrunch and open up the class heights data file and make your histogram for the heights of students in the class. When you do that, make the histogram for the heights of students in the class, you should get something that looks like this. We've seen this histogram before. Notice the lack of a general bell shape and the presence of no outliers. Well, actually, it depends on how you do the actual bend lengths, because, yeah, we do have what may be a couple of outliers here, but definitely there's some skewness to the distribution itself. Of course, the real proof is the normal quantile plot. So go ahead, pause the video, and then make your normal quantile plot in StatCrunch, and then let's compare and see how you did. Okay, so when you make the normal quantile plot in StatCrunch, you should get something that looks like this. Here we have data points that are not conforming to the general line. First of all, you've got your two outliers right here, and then some of these data points, yeah, many of them are fairly close to the line. These points out here in this area, you kind of, it's yes, kind of no, sort of on the fence with that. But generally with the two outliers, yeah, you would say this is not normally distributed. Let's talk for a moment about data transformations, because we find that many real-world data sets are not normally distributed. But if we can only figure out how to transform the data set so that they are normally distributed, then we could use the tools in our toolbox that we've learned in Chapter 6 for normal distributions. So there's a lot of emphasis in the real world on taking data sets that don't conform to a normal distribution and transforming the data such that the transformed data then is normally distributed, because then that lets us use all the nice little tools in our toolbox for looking at probabilities and the such. So we take data sets that don't have a normal distribution and we apply some transformation to it. So the values are modified to have a normal distribution. There's a very common transformation to replace each value of x with the log base 10 of x plus 1. And we add 1 to the x before taking the logarithm, because very often in real world data sets, one of our data values for our random variable x is 0. And if you take the logarithm of 0, you get an undefined result. So we don't want that to bung up the works, so to speak. So we just go ahead and add 1 to each of our data values, and then taking the logarithm is no problem. If the distribution of the log x plus 1 values is a normal distribution, then we would call that distribution of x values a log normal distribution. So called because we applied a logarithm to make the distribution normal. There are many other types of transformations, and depending upon what field you go into and what area you're actually looking at, some transformations are going to be more popular than others. The log transformation is a pretty common one across disciplines, but there's some other common ones too, such as taking the square root of x, or taking the reciprocal of x, or taking the square of x. There's a whole host of possibilities at our disposal, so we have many choices for making data transformations. Now, before we go on to looking at some examples, I want to point out that in the real world, much of this data transformation business is handled with software. Thank goodness we live in the 21st century, right? Because see, now we have software that does all of this stuff for us. So what we're going to do is learn a little bit of the old school way of doing this. And it's important to learn the old school way because we need to understand what the software is doing in the background, so we're not just pushing buttons, but we can actually interpret the result that the computer software gives to us. Let's look at how to do this in StatCrunch, and this is the actual software that we're actually going to be using. So let's learn how to do this in StatCrunch. Could we transform the data from our class height data set so that they are normally distributed? Well, let's find out. What do we get with each of the following transformations? So we're going to try and apply each of these transformations to our data set to see if it makes the data set normally distributed. First, we're going to add 10 to each value. Then we're going to try converting inches to centimeters. Then we're going to take the reciprocal of each value. And finally, we're going to end up taking the logarithm of each value. So let's look and see what each of these transformations does to our data set, and also how to actually do them in StatCrunch. The way that we actually perform data transformations in StatCrunch is to first place your cursor in the first cell of the column where you want your transformed data to appear. Typically, I just pick the next free column over. Then you want to go up to Data, come down to Compute, and then hit on Expression. When you do that, you're going to get a nice little window for your options window. It's going to pop up and look something like this. You can actually type the expression that you want to perform the transformation into the expression field here. The other option you have is to press on the Build button you see there at the end. That's the option that I like to do because we all know the computers are very sensitive to syntax and how you put things into, how you input values into them. So in order to avoid potential errors with syntax, I just go ahead and just hit Build so that I get a nice little builder window that pops up here, and then I can use this builder window to build my expression so that the syntax that I use is actually appropriate. So inside this builder window, first what you want to do, because we're going to add 10 to each of our values. So first select the column that we want, and you do that by selecting a column and then press Add Column. Simply selecting the column alone is insufficient. You've got to select the column and then press Add Column so it will pop up here in the expression field. Then you're going to type in +10. You can use it with your keyboard, or you can use the little mini keyboard that you see here on the expression window. Press OK, and then you'll go back to this expression, to this options window, and the expression that you entered in will appear here in the expression field. Go ahead and press Compute down here in the lower right corner, and your data set gets populated with a new column. And notice how each of the values, this is where you had your cursor, so notice how each of the values have 10 added to it. So 62 becomes 72, 76 becomes 86, 67 becomes 77, so on and so forth. So this is how you actually perform transformations of your data in StatCrunch. Note that each value, as I just pointed out, is 10 more than the corresponding value from the original data column. Also notice that StatCrunch automatically name the column of the transformed data. Now, in the previous slide, I showed you the expression window, and right under where the expression appears, there's another field for column name. It's optional. You don't have to fill it in. I typically don't fill it in, but if you wanted to name it something special, you could put the name of the column in there. Alternatively, you could also click on the column header and then delete whatever StatCrunch has there, and then type in your own column name. So there's different ways to go about it. Typically, I don't mess with that. The reason being is that the default name that StatCrunch gives to these transformed data columns tells you, one, the data column for the original data, and two, what transformation was applied to it. It uses these two pieces of information to form the name of the transformed data column. That can be very useful when you have several transformations of the same data set on the same data table. It makes it easier to distinguish which transformed data set is which. So typically, I'm not going to mess with the default setting there. I'm just going to let StatCrunch do its thing. Now that we have our transformed data, we can make a new normal quantile plot and check for normality in the transformed data. So go into Graph, QQplot, and up pops this nice little window. Remember, you need to select the transformed column because that's what we want to test for normality. And then go ahead and remember to check this box for normal quantiles on the y-axis. Again, I don't know why that's not a default feature, but that's what you need to check on. Click Compute down at the bottom, and you'll get a normal quantile plot that looks something like this. Again, we see that we're lacking normality because we've got the outliers here and the same general shape for our data points here on the plot. So essentially all adding 10 did was give us a shift in the data. It didn't actually transform everything, it just shifted everything horizontally. So no real change here for the assessment of normality. These points do not conform to the straight red line in the plot, so we can say our data are not normally distributed. What happens if we convert from inches to centimeters? Will this make our data normally distributed? Well, there's about 2.54 centimeters in every inch. So to convert from inches to centimeters, we have to multiply each of our values in the original data set by 2.54. So again, place your cursor in the top cell of the column where you want the transformed data to appear. Then go to Data, Compute, Expression. And in the expression window, go ahead and hit on Build so you get this expression builder. And go ahead and build the expression. So we're going to select the original data set, height of inches, press Add Column, and then look, we get that here into our expression field. Then go ahead and press times 2.54, click on OK, and then click on Compute in the next window that follows, and we have what we need to construct our new normal quantile plot. When we do, we get something that looks like this. So again, we see the same general shape to this. So multiplying by a certain factor is not going to change the general shape of our data points here that they're being made in a normal quantile plot. So again, we find the points are not conforming to a straight red line, so the data are not normally distributed. What if we take the reciprocal of each value? So taking the reciprocal means that we take each value and divide it into 1. So essentially, we're making a fraction where 1 is on the top and our original value is on the bottom. Again, start by placing your cursor in the top cell of the column for the transformed data. Then go to Data, Compute, Expression. When you get to your expression builder, type in 1 and then press the slash button and then add in the column height inches. Press Add Column so it adds it in, then go ahead, once you have that expression built, go ahead and press OK, and then Compute in the next window, and we have what we need to construct a new normal quantile plot. So in StatCrunch, go to Graph, QQ Plot, and construct the new normal quantile plot. When you do, you get something that looks like this. So taking the reciprocal will change the shape of our data set. Or will it? Look at the two outliers that we have down here, sort of like the two outliers that used to be up here. And these points that are now below the line used to be above the line. So essentially, what taking the reciprocal does is it basically flips the data points around on your graph. So what was up and to the right is now down and to the left. So this really didn't help us much with making a normal distribution in our data set, because still the points are not conforming to that straight red line in the plot. So reciprocals don't really help us to make this data set normally distributed. What about taking the logarithm? And this is a base 10 logarithm for each value in our original data set. I specify base 10 because you're going to see that StatCrunch has a number of different logarithm options for you to use. Again, start by placing your cursor in the top cell of the column where you want your transform data to appear. Then go to Data, Compute, Expression. Once you get to your Expression Builder window, make sure that you go here and in the list of functions, go ahead and scroll down and notice how we've got several different options for log. There's a general log function, there's a log 10, log 2, and log beta. Go ahead and press the log function that you see right here. I'm not really clear on what's the difference between log and log 10, because a general log function has an assumed base of 10. So why they would make a separate function for log 10, I'm still unclear on. Perhaps one day when I get the answer, I'll share it with you, but that day has to come first, and that day is not today. Anyway, when you want to take the log function, just go ahead and select this general log function. Don't worry about the others. When you do that, the cursor will appear on this second part of your parenthesis, indicating that it's waiting for you to put stuff into the parenthesis. So go ahead and in this column, select the column for your original data set, click on Add Column, so it adds it into our logarithm function. Now, don't worry about adding one or performing any further transformation on the data. We don't have anyone in the class whose height is 0. So there's no need to make any further transformation on the data set. Just go ahead and just use the logarithm. And once you have that, go ahead, you have your expression built, so go ahead and click on OK, and then Compute in the Options window, and you have the data set that you need now for making a new normal quantile plot. So then in StatCrunch, go ahead and go into Graph, QQ Plot, and select the data for the newly transformed data set for your logarithm. You may have to scroll down in the window to see it, but then select it and make sure you also check that box to put the quantiles on the y-axis. Once you do that, you have what you need. Go ahead and click Compute, and out pops this lovely normal quantile window that you see here. So some slight adjustment, it seems, has been made, but not a whole lot. So taking the logarithm of this particular data set didn't really do much for us. So once again, we say these points do not conform to a straight red line, and so they are not normally distributed. There are instances in the real world where no real data transformation that you do is going to make it normally distributed. The beautiful part about having this process encoded in software is that when we do this old school, it's kind of hit and miss. And you got to go through multiple iterations before you figure out which way is the right one. So this is something that's actually done by people who are very experienced in it, because they've done it so many times that they can intuitively sense what the right choices are to get you to the data transformation you need as quickly as possible. Computers are able to run through multiple iterations very, very quickly. So having something like this encoded into a computer software program is wonderful, because almost instantaneously you can get the data transformation that you need to get where you want to go. So it's wonderful living in the 21st century because the software handles a lot of stuff for us. But it's good to know what's going on in the background so we know how to interpret the information that we're given. Let's look at a real-world example involving earthquakes. There should be a data file in our class group set entitled Earthquakes. So if you want, go ahead and pause the video and open up that data file in StatCrunch, and you can follow along with this example. The energy level from earthquakes has been measured and converted to a Richter scale magnitude for reporting and comparison purposes. The question is, are the energy levels normally distributed? Well, as I mentioned before, in our StatCrunch group, there's a file called Earthquakes. So once you have that open, you notice that the original data set contains measurements for energy level and depth. So what we want to do is use the column for the energy level to see if those values are normally distributed. Remember, first construct a histogram and then construct a normal quantile plot using the energy level data. So if you like, pause the video for a moment, make your plots, and then restart the video and let's see how you did. Alright, so when you make your histogram and normal quantile plot for the energy level data in the earthquakes data file, you should get something that looks like this. So here's our histogram. Looking on the right, very skewed, one outlier way out here on the end. We can see that outlier out here to the far right in our normal quantile plot, and look at the shape that's being made in our normal quantile plot. We have that curved line feature that is corresponding to a skew distribution, which is what we see in our histogram. So very clearly here we see the points do not conform to a straight red line in the plot. So these data are not normally distributed. Now the question becomes, if we convert them to this Richter scale and apply a log normal data transformation, will our data set then become normally distributed? Well, first let's apply the data transformation so we can get our values. Place your cursor in the top cell of the column where you want the transform data to appear. Typically, I just pick the next free, open, and clear category, column. Then go to Data, Compute, Expression, and go ahead and press on Build so you can get to the expression builder. And when you get there, go ahead and select Log again from your function window, press Add Function, and then in the columns, go ahead and select Energy, and then Add Column. I should end up with something that looks like this. Once you get that, go ahead, your expression is built, so go ahead and click OK, and then click Compute in the Options window, and you have your values for data that's been transformed. Now we're asking, are the transformed data values normally distributed? Well, we can easily find out. Again, we make our histogram and our normal quantile plot. And when we do, we get something that looks like this. Feel free to make these graphs in StatCrunch. You should be comfortable with how to do that. Go to Graph, Histogram, or go to Graph and the normal, QQ plot to make these two graphs. And don't forget to select the proper options for the QQ plot. You got to check that box for putting the quantiles on the y-axis. But once you do, you get plots that look like this. So now we see more of a general bell curve shape with our histogram. We don't see the outliers that we saw before, although it could be argued that this value here on the right is still an outlier. There's other statistical measures that we could use. Remember when we were making box plots, we can actually use some of the criteria for making box plots to determine if this value here on the far right is truly an outlier. But be that as it may, it's only one, and we're allowed to have one outlier when assessing normality. Other than that, these points are generally conforming to this red line that you see in the straight line pattern, and We're not seeing a lot of deviation from that, so no other standard shapes. There's no sinusoidal shape, no curved lines. So what we would assess is that, yes, generally, these data points are conforming to that straight red line, and so the transformed data set is normally distributed. So here's a real-world example where a data set that was not normally distributed now becomes normally distributed, and now we can pull out all the statistical tools from our toolbox that we've learned here in Chapter 6 and apply them to this particular example. That brings us to the end of this lecture. If you have any questions, you know what you need to do. Otherwise, I will see you in class or the next video. Thanks for watching.